Hello students, I'm Mayur Naik, a professor of computer science at Georgia Tech. Welcome to Software Analysis and Testing. In this course, we will be diving deep into the theory and practice of software analysis, which lies at the heart of many software development processes, such as diagnosing bugs, testing, debugging, and more. What this class won't do is teach you basic concepts of programming. Instead, through a mixture of basic and advanced exercises and examples, you will learn techniques and tools to enhance your existing programming skills and build better software. So why should you take this course? Bill Gates once said, and I quote, "We have as many testers as we have developers, and testers spend all their time testing and developers spend half their time testing. We are more of a quality software organization than we are a software organization." In this course, you will learn modern methods for improving software quality in a broad sense, encompassing reliability, security, and performance. This will enable you to become a better and more productive software developer, as the aspects that we will address in this course, such as software testing and debugging, comprise over 50% of the cost of software development. You will also be able to implement these methods in specialized tools for software diagnosis and testing tasks. An example task is systematically testing an Android application in various end-user scenarios. But let's face it, you are really here for the war stories. The Ariane rocket disaster of 1996 is a war story of epic proportions. Here is a video of the maiden launch of the Ariane rocket in 1996 by the European Space Agency. Roughly 40 seconds after the launch, the rocket reaches an altitude of 2.5 miles. But then it abruptly changes course and triggers a self-destruct mechanism, destroying its payload of expensive scientific satellites. So why did this happen, and what was the aftermath of this disaster? Let's take a look. The cause of the disaster was diagnosed to be a kind of programming error called a numeric overflow error in a program running on the Ariane rocket's onboard computer. The error resulted from an attempt during takeoff to convert one piece of data, the sideways velocity of the rocket, from a 64-bit format to a 16-bit format. The number was too big to fit and resulted in an overflow error. This error was misinterpreted by the rocket's onboard computer as a signal to change the course of the rocket. This failure translated into millions of dollars in lost assets and several years of setbacks for the Ariane program. The methods that we will learn in this course could have prevented this error. To read more about this disaster, access the link provided in the instructor notes. Now let's look at another problem that is more earthly and affects everyday users of software. While the Ariane disaster was a consequence of a programming error, at least the damage was an unintended consequence. On the other hand, malicious hackers can exploit these errors in everyday mobile and web applications to compromise the security of the underlying systems and data. This is a widespread problem, and it has been since the early days of the internet. Several examples of programming bugs leading to security vulnerabilities you may have heard of include Moonlight Maze, which probed American computer systems for at least 2 years since 1998, Code Red, which affected hundreds of thousands of Microsoft web servers in 2001, Titan Rain, a series of coordinated attacks on American computer systems for 3 years since 2003, and most recently, Stuxnet, a computer worm that shut down Iranian nuclear facilities in 2010. And the problem has only gotten worse with the advent of smartphones. Now you too can make yourself vulnerable to programming disasters simply by installing an app. Program analysis is the process of automatically discovering useful facts about programs. An example of a useful fact is a programming error. We saw an example of a programming error that was responsible for the Ariane disaster and others that underlie security vulnerabilities. Program analysis as a whole can be broadly classified into 3 kinds of analyses: dynamic, static, and hybrid. Dynamic analysis is the class of runtime analyses. These analyses discover information by running the program and observing its behavior. Static analysis is the class of compile time analyses. These analyses discover information by inspecting the source code or binary code of the program. Hybrid analyses combine aspects of both dynamic and static analyses by combining runtime and compile time information in interesting ways. Let's take a closer look at dynamic and static analyses. Dynamic program analysis infers facts about a program by monitoring its runs. Here are 4 examples of well-known dynamic analysis tools. Purify is a dynamic analysis tool for checking memory accesses such as array bounds in C and C++ programs. Valgrind is a dynamic analysis tool for detecting memory leaks in x86 binary programs. A memory leak occurs when a program fails to release memory that it no longer needs. Eraser is a dynamic analysis tool for detecting data races in concurrent programs. A data race is a condition in which 2 threads in a concurrent program attempt to simultaneously access the same memory location, and at least one of those accesses is a write. Data races typically indicate programming errors, as the order in which the accesses in a data race occur can produce different results from run to run. Finally, DICON is a dynamic analysis tool for finding likely invariants. An invariant is a program fact that is true in every run of the program. Static program analysis infers facts about a program by inspecting its code. Here are 4 examples of well-known static analysis tools. Tools such as lint, find bugs, and coverity inspect the source code of C++ or Java programs for suspicious error patterns. SLAM is a tool from Microsoft that checks whether C programs respect API usage rules. This tool is used by Windows developers to check whether device drivers use the API of the Windows kernel correctly. Facebook Infer is a more recent static analysis tool developed by Facebook for detecting memory leaks in Android applications. Finally, ESC Java is a tool for specifying and verifying invariants in Java programs. We will look at an example of an invariant next. Let's do the following exercise to illustrate a concrete example of a useful program fact, namely a program invariant. Consider the following program, which reads a character from the input using function getC. If the input is the character A, it takes the true branch. Otherwise, it takes the false branch. Recall that an invariant is a program fact that is true in every run of the program. An invariant at the end of this example program is z equals c for some constant c. What is c? Take your time and enter the value of c in this box. The value of c is 42. To see why, we need to reason about only 2 cases over all runs of this program. In the runs where the true branch is taken, the value of z is p of 6 plus 6, which is 36 plus 6, which is 42. In the runs where the false branch is taken, the value of z is p of minus 7 minus 7, which is 49 minus 7, which is 42 again. Thus, the value of c is 42. We have thus shown that z equals 42 is a program invariant at the exit of this program. Now let us slightly change this program to call disaster whenever the value of z is not equal to 42. Then, notice that the invariant we just discovered is a useful fact for proving that this program can never call disaster. Now let's see how different kinds of program analyses fare at discovering program invariants. Let's first consider dynamic analysis. For simplicity, the shown program has only 2 paths. But in general, programs have loops or recursion, which can lead to arbitrarily many paths. Since dynamic analysis discovers information by running the program a finite number of times, it cannot in general discover information that requires observing an unbounded number of paths. As a result, a dynamic analysis tool like DICON can at best detect likely invariants. From any run of the shown program, DICON can at best conclude that z equals 42 is a likely invariant. It cannot prove that z will always be 42 and that the call to disaster can never happen. This is not to say that dynamic analysis is useless. For one, the information that z might be 42 could be a useful fact. More importantly, DICON can conclusively rule out entire classes of invariants even by observing a single run. For instance, from any run of this example program, DICON can conclude that z equals c is definitely not an invariant for any c other than 42, such as 30. On the other hand, to conclusively determine that z equals 42 is an invariant and therefore showing that the program will never call disaster, we need static analysis. Now let's consider how static analysis works on this example. Static analysis can conclusively say that z equals 42 is an invariant by inspecting the source code of the program. The reasoning it applies is similar to what we ourselves used in the quiz. Recall that we too inspected the source code to determine that the constant c has value 42. Static analysis can therefore show at compile time that the program will never call disaster at runtime. You should now be able to see how the Ariane disaster could have been averted using static analysis. Let's first introduce common terminology. Static analysis typically operates on a suitable intermediate representation of the program. One such representation shown here is a control flow graph. It is a graph that summarizes the flow of control in all possible runs of the program. Each node in the graph corresponds to a unique statement in the program, and each edge outgoing from a node denotes a possible successor of that node in some execution. To achieve its stated goal, our static analysis tracks the constant values of the three variables in this program, x, y, and z, at each program point. This is called an abstract state in contrast to a concrete state, which tracks the actual values in a particular run. Since static analysis does not run the program, it does not operate directly over concrete states. Instead, it operates over abstract states, each of which summarizes a set of concrete states. As a result of this summarization, the static analysis may fail to accurately represent the value of a variable in an abstract state, which we denote using a question mark. While this ensures the termination of the static analysis even for programs with an unbounded number of paths, it can also lead the static analysis to miss variables that have a constant value. For this reason, we say that the static analysis sacrifices completeness. Conversely, whenever the analysis concludes that a variable has a constant value, this conclusion is indeed correct in all runs of the program. For this reason, we say that the static analysis is sound. Now let's examine how static analysis discovers invariants of the form z equals 42 even for programs that have an unbounded number of paths. We can pose this question in terms of a classic static analysis problem. This problem aims to find variables that have a constant value at a given program point. Consider the following example program which contains a loop. We will explain step by step how a static analysis discovers that the variable y has the constant value 7 at the exit of this program. We use a common static analysis method called iterative approximation. The analysis begins with unknown values for the three variables at the entry of the program. At each step, the analysis updates its knowledge about the values of the three variables at each program point. The analysis does this update based upon the information that it has inferred at the immediate predecessors of that program point. For instance, after the statement that assigns 3 to z, the analysis knows that the value of z is the constant 3. Another interesting update occurs in the true branch of the condition that checks whether the value of x is 1. After taking this branch, the analysis knows that the value of x must be the constant 1. Notice that in the false branch of this condition, the analysis does not know whether x has a constant value in all runs of this program. So it continues to indicate that the value of x is unknown. Similarly, after the statement that assigns 7 to y, the analysis knows that the value of y is the constant 7. The analysis has thus concluded that every time this program point is reached in any run, x has value 1, y has value 7, and z has value 3. Now let's look at the statement that assigns the expression z plus 4 to y. Since the analysis had previously discovered that the value of z before this statement is the constant 3, it can conclude that the value of y after this statement must be 3 plus 4, which is 7. At this point, the analysis has concluded that at each immediate predecessor of the assertion, the value of y is 7. It thereby concludes that the value of y in the assertion must be 7 and therefore that this assertion is valid. The term iterative approximation implies that, in general, the analysis might need to visit the same program point multiple times. This is because of the presence of loops, which can require the analysis to update facts that were previously inferred by the analysis at the same program point. We will emphasize this aspect in the following quiz. Consider the following program. The analysis begins with an unknown value for variable b at the start of this program. In each of the 3 boxes shown, fill in the value of variable b that the analysis infers at the corresponding program point after completing its analysis. We will call these program points the loop header, the entry of the loop body, and the exit of the loop body. If the analysis cannot infer a definite value for b, enter a question mark into the box. Immediately after the assignment of 1 to b, our static analysis knows that the value of b is 1. Therefore, the value of b in the first box is 1. As the analysis proceeds, it discovers that the value of b at the entry of the loop body is still 1. Similarly, it discovers that the value of b at the exit of the loop body is 2. But the analysis is not done yet. It must analyze the loop again to ensure that these values are indeed sound. The analysis revisits the entry of the loop body. This time, it notices that the value of b can be either 1 or 2. So it updates the value of b at the entry of the loop body to unknown. Continuing further, the analysis updates the value of b at the exit of the loop body to unknown as well. Due to these updates, the analysis analyzes the loop yet again, but this time it concludes that the values of b at the entry and the exit of the loop body have saturated. Therefore, the correct value of b in the second and third boxes is the unknown value. Okay, time for another quiz. Dynamic and static analyses strike different trade-offs in terms of their cost and effectiveness. Match each box with its corresponding feature. Let's review the answers. First, we will focus on cost. Since dynamic analysis gathers information by running the program, its cost is proportional to the execution time of the program. A longer run thus costs more than a shorter one. Static analysis, on the other hand, gathers information by inspecting the program's code, and therefore its cost is proportional to the size of the program's source code. A larger program thus costs more than a smaller one. Now let's look at effectiveness. As we saw in the example about program invariants, a dynamic analysis may miss errors, as it inspects only a finite number of runs, whereas the program may contain an unbounded number of paths, some of which are not covered by those runs. We say that a dynamic analysis is unsound. In other words, it may produce false negatives. Static analysis, on the other hand, does not miss errors, but it may report spurious issues. We say that a static analysis is incomplete. In other words, it may produce false positives. You might be wondering whether it is possible for a program analysis to guarantee both soundness and completeness. No false positives nor false negatives. The answer is not if we want the analysis to eventually finish. Even seemingly simple program properties for realistic programming languages like C and Java are undecidable. An example such property is whether a given program point is reachable on some input to that program. You can find a link to recommended reading on the topic of undecidability in the instructor notes. Designing a program analysis is thus an art that involves striking a suitable trade-off between termination, soundness, and completeness. This trade-off is typically dictated by the consumer of the program analysis. Let's look at the primary consumers of program analysis next. There are 3 primary consumers of program analysis: compilers, software quality tools, and integrated development environments, or IDEs for short. Compilers bridge the gap between high-level programming languages and advanced computer architectures. They use program analyses to generate efficient code on a target architecture for programs written in a high-level source language. Let us see a simple example of how a program analysis can help a compiler generate efficient code. Consider this example program. We saw earlier in this lesson how a static analysis can discover the program invariant z equals 42 at the end of this program. A compiler can use this invariant to simplify this program. The simplified program simply prints 42. It is easy to see that this simplified program is more efficient than the original program. It runs faster, it is more energy efficient, and it is smaller in size. The second key consumer of program analysis is software quality tools, which will be the primary focus of this course. This category broadly includes tools that programmers use for tasks to improve software quality, such as testing, debugging, and verification. These tools use program analysis for various purposes, such as finding programming errors, proving program invariants, generating test cases, and localizing the causes of errors. Consider this example program again. The invariant z equals 42 discovered at this program point by a static analysis could be used by a program verification tool to prove that this program can never call disaster. The third main consumer of program analysis is integrated development environments, such as Eclipse or Microsoft Visual Studio. Such environments use program analysis to help programmers understand programs and refactor programs, which is the process of restructuring a program without changing its external behavior. These features are especially needed when dealing with large, complex programs which are common in practice. Let's recap the main topics that we have covered in this lesson. First, we introduced program analysis, a process for automatically discovering useful facts about programs. We then discussed two kinds of program analyses, dynamic and static analysis. The primary difference between these two kinds of analyses is that dynamic analysis works by running the program, whereas static analysis works by inspecting the program's code. We discussed the pros and cons of these two kinds of analyses. We discussed how dynamic analysis can discover likely invariants and how static analysis can prove invariants. We also saw step by step how static analysis can prove a certain kind of program invariant using the method of iterative approximation. We learned that the undecidability of even simple program properties prevents program analyses from simultaneously guaranteeing the three desirable features of termination, soundness, and completeness. Finally, we discussed the three main consumers of program analysis: compilers, software quality tools, and integrated development environments.